Okay, I'm going to teach you how to solve every type of Bohr model problem. And before we start, we have to really look at what's happening inside the atom. So basically what we have is our nucleus, and then each of these concentric circles represents an orbit that the electron can be in. Now, the very first level, when we're talking about hydrogen, is called n equals 1, and this is known as the ground state. And then the rest of them are super easy. It's just n equals 2, n equals 3, and so on. N equals 4. Okay, there's actually more levels, but we're just going to do it for this. So what happens is this. Let's say we have an electron that's hanging out in this level n equals 2. If the electron jumps down a level, so it's jumping from n equals 2 to n equals 1, it will emit a photon. Now, what is a photon? It is a little bundle of energy that has a specific frequency. Remember, and it acts like a wave and a particle. So this gets ejected. So the first idea is that when an electron jumps down, a photon gets emitted. And the energy of the photon is equal to the difference in the energy levels. So this energy level has a different energy than this level. Now what we do is we say that these energies are negative, because you can think of it as being down in a well. When you're down here at the bottom level, you have negative energy. You're trapped within this atom. So if I make up a number and say n equals 1 is equal to negative 6 EVs, and this level is negative 4 EVs, then the difference, just ignore the minus signs, the difference is 2 EVs. So this photon will have an energy of 2 electron volts. Now, it could jump from a higher level. It could jump from n equals, 3 to n equals 1, and that would emit a photon of higher energy. But what about going up? Well, you could also have an electron where a photon goes into it, it is absorbed, and it jumps up a level. Now, for this to happen, it has to absorb a photon that's exactly equal to the difference between the levels. If it's too much, let's say enough to make it to go to here, it will just fall back down. If it's enough to make it to here, then it will end up going to that energy level. So what are the key ideas? The key ideas are this. Number one, when an electron jumps down, we're talking about down a level, a photon is emitted. That's emission. That means given off. When a photon is absorbed, that means the electron takes a photon into it. The electron will jump up a level. Now, this will only happen if the absorbed photon is equal to the energy between the levels. And I'll give you some examples with numbers of that next. And then finally, the energy of the photon, so this is the photon that's either absorbed or emitted, is equal to the energy difference, the subtraction between the levels. And that number we can use to actually calculate the frequency. So now we're going to look at some examples with numbers. So when we look at these levels, these are the parts of the circle. So when we had this circle like this, we're looking at a segment of this with each line. So each of these lines represents a level, and the nucleus would be down here, but we don't really care about that. So the lowest level we said was called the ground state, n equals 1, and that I'm making up some numbers here to make it really simple. So we'll deal with the decimals later, but let's just deal with some whole numbers so we can see how the math works. So negative 10 EVs is our ground state. And why this is negative is because the electron is trapped within the atom. So the amount of energy that's needed to get the electron completely out of the atom is 10 electron volts. So if it's here, it needs 6 to get out, 2 to get out, 1 to get out. So what does that mean when an electron gets out? What does that getting out part mean? Well, if you remember from chemistry, when you get rid of an electron, it's ionized. Therefore, these are all called ionization energies. So these are the levels of ionization. So let's say we have an electron that jumps from n equals 2 down to n equals 1. So we have an electron right here, and it jumps down a level into n equals 1. What's going to happen? Well, we know that jumping down means that there's going to be emission. Emission when you jump down, absorption when you jump up. So we have emission. Emission of what? A photon gets released. And how do we do that? Well, ignore the negative signs and just look at the difference. The difference between 10 and 6 is 4 electron volts. So the energy is 4 EVs. Now, the problem with this is that it's in electron volts, and our formula that uses frequency uses a constant, Planck's constant, which is joule seconds. So we have to convert that to joules. And if you do that conversion, I'll show you how to do that. We'll do a whole problem with all the steps later. But that gives you an energy of 6.4 times 10 to the minus 19th joules. And then we can do E equals HF to find the frequency, and the frequency gives us the color of the emitted photon. So let's say we have an electron in n equals 1, so we have an electron here, and it's hit with 5 electron volts. So 5 electron volts, this photon comes in, hits it, 5 electron volts. If it was hit by one with 4, it would jump up to here, because that's the difference between the levels. But 5 is not enough to get it to n equals 3, because from 10 to 2, that would be 8. So it gives it 5. So all it's going to do is go up and fall back down to this level. It's not going to go anywhere. Okay, if it was exactly 4, then it would absorb it and go up. If it was exactly 8, it would absorb it and go up to here. Okay, so if an electron is n equals 4 and jumps down to n equals 1, I'm just going through every different combination that you could have. That's jumping from 1 to 10, so that's a difference of 9 electron volts. So this emitted photon would be 9 EVs. So here's another question you could get asked. How much energy does an electron in n equals 2 need to escape the atom? In other words, to be ionized. Well, if we have an electron here and we want to get it out, then we need to give it at least 6 electron volts. But let's say this is a rare question, but it could come up. What if they gave this electron, I'll make up a number, 8.5 electron volts? Well, it only needs 6 to get out, but there's 1.5 electron volts left over. So they could ask you, what's the excess energy? The electron would have an excess kinetic energy of 1.5 EVs. So let's do an entire problem from start to finish. So the question is, what color photon is emitted when an electron jumps from n equals 3 to n equals 2 in hydrogen? Okay, so what we're looking for is the color of the photon that is emitted. Now, why is it emitted? Because it's jumping down a level. So what we need is the chart for hydrogen in the energy level diagram. So that looks like this. Now, we're jumping from 3 to 2. So we're going to go from 3, which is negative 1.51, to n equals 2, which is negative 3.4. Ignore your minus signs. We're just finding the difference. And so we're going from 3.4 EVs to 1.51 EVs. Actually, we're going the other way, but it doesn't matter because we're finding the difference. So what's the difference? Just subtract that, and the energy of the photon comes out to 1.89 electron volts. Well, we know that our formula E equals HF, our constant is in joule seconds, so we have to convert that to joules. So how do we do that? We just do 1.89 EVs and multiply that by 1.6 times 10 to the minus 19th joules per electron volt. That's our conversion. And that gives us 3.02 times 10 to the minus 19th joules. Now that we have this in joules, we can do E equals hf. Remember, that's energy of the photon, and that's Planck's constant. So Planck's constant is on the reference table, and it's right here, 6.63 times 10 to the minus 34th. So all we have to do is put our energy in, which is 3.02 times 10 to the minus 19th joules equals 6.63 times 10 to the minus 34th joules seconds times F. And when you multiply through, or actually divide through, you get 4.56 times 10 to the 14th hertz. So what is that? Well, if we look at our chart here, 4.56 is right in between this range, so that's red. So our answer is a red photon. So what was the original question? It says, what color is emitted from 3 to 2? We found the difference in the energy levels. We took that number and converted it to joules, and then used E equals hf to find the frequency, and we looked up the frequency on the chart to find out that the color was red. So let's say that now, instead of being asked to find it jumping from 3 to 2, you're asked to find it from 4 to 2. Okay, and we're doing this for hydrogen right now. We'll do this for mercury later. So from 4 to 2, so we look up our 4, and that is 0.85 electron volts, and our n equals 2, that's 3.4. So we're going to find the difference between these two. So 0.85 to 3.4, we just get rid of the negative signs and subtract, find the difference. So this is the energy of the emitted photon. We then need to convert from electron volts to joules. So if you forget that, it is on the reference table that 1 electron volt is 1.6 times 10 to the minus 19th joules. So we cross multiply, our EVs cancel, and we're left with 4.08 times 10 to the minus 19th joules. This is now in joules, so we can use E equals hf. H is on the reference table, Planck's constant. Solve for the frequency, and we get 6.15 times 10 to the 14th hertz. Now, I want to point something out here. This is 6.15, so it's on the blue, it's in the blue spectrum, but it's close to green. So it's more of an aqua shade. It's definitely blue, but it's more on the aqua shade. So the jump from 3 to 2 was red. The jump from 4 to 2 was bluish green. What's it going to be for the other two jumps? So if we do hydrogen from 5 to 2, we look up the numbers, we subtract them, do our conversion, and use E equals hf to get the frequency. So we did 2 of those. I'm not going to do it all over again. It's the same exact process. And what you get is violet. And violet, it's actually violet but very close to the blue side. So it's still violet, but it's violet with a little bit of a bluish hue to it. And then if we look at n equals 6 to n equals 2, that jump is going to be 0.38 EVs to 3.4. We subtract them, do our conversion, and our E equals hf, and we get a frequency of 7.3 times 10 to the 14th, which is also violet, but it's violet closer to the ultraviolet side of the spectrum. So let's look at the jumps that we just did. We did all of the jumps down to n equals 2. I intentionally did not do the jumps down to n equals 1, the ground state, for a reason, and you'll see why in a minute. So we did the calculation for the jump from 3 to 2. What did that do? It emitted a photon, and that photon was red. Then we did the jump from 4 to 2, and that emitted a photon that was bluish green or aqua. And then we did the jump from 5 to 2, and that was ultraviolet, so a little higher frequency. And then this jump from 6 to 2 was also violet, but closer to ultraviolet, so even higher frequency. The name of the jumps that all end up at 2 have a name, and the name of those jumps are called the Balmer Series. Now, why is this important that we did the jumps to 2? Well, the jumps to 2 are all visible. We can see red, we can see blue, we can see violet. So the person who first discovered these jumps was a guy named Balmer, and he was the one that discovered these first because they were the ones that were in the visible spectrum, because you could see them. So the name of this is called the emission spectrum. So if we have this black background, we can see that it will give off, when you look at this through a diffraction grating separate all the colors out, you'll see red, bluish green, and the 2 violet strips. Here's what it looks like. So we have our continuous spectrum, which would be all of the colors, but the emission spectrum would only give us the colors that are emitted. So that would be a black background, then the colors that are emitted, red, aqua, and our 2 violets. If we do the opposite of this, if instead we take a cool gas, we take hydrogen and it's cool, and we hit it with all the different colors of light, so we hit it with the full spectrum of the rainbow, instead of these all jumping down, then they would all jump up. And these jumps up produce something called an absorption spectrum. So the Balmer series that we just looked at was the emission spectrum, but if we take something that's absorbing from the colors, then what we end up with is a rainbow, but the colors that are absorbed appear black because they are getting sucked in by the hydrogen atom and we can no longer see them. So we can see the hydrogen emission spectrum above. The absorption spectrum is the full rainbow, the full spectrum, minus the photons that were absorbed. So we're seeing a black strip where there is absorption of red, aqua, and our 2 violets. So we saw that the Balmer series was all of the jumps from 6 to 2, 5 to 2, 4 to 2, and 3 to 2. But what about the jumps that jump down to the ground state? Let's first take n equals 2 to n equals 1. Now, if you notice, this is a huge jump. This is from 3.4 electron volts to 13.6 electron volts. So in that jump, we're jumping from 2 to 1. We're going from 3.4 to 13.6. How do we do it? We subtract them to find the difference. That's the energy of the photon. The problem is it's in electron volts, so we convert. We use our conversion factor to get the answer in joules. Once we have it in joules, we can use E equals HF, and we put in Planck's constant and solve for the frequency. So why wasn't this discovered first? Well, because this is in the ultraviolet range of the spectrum. So if you look at this exponent, 2.4 times 10 to the 15th, that is above violet. What's above violet? Ultraviolet. So all of the jumps that jump from 2 to 1, 3 to 1, 4 to 1, 5 to 1, 6 to 1, all of these are giant jumps with lots of energy, so all of these are ultraviolet. And the name of this series is called the Lyman series. Now, we don't have to keep doing all of these, but as you can see, that if we're going to do smaller jumps, we did the jumps that all ended in 2, those were the Balmer. We did all the jumps that ended in 1, that was the Lyman. What about all these short jumps, though? And when we look at the levels, up here the levels are very compressed. So these little tiny jumps are going to have little tiny energies. Well, if the energy is very small, let's say, I don't know, some of these are like 0.5 electron volts, that's not a lot of energy. So when we do E equals HF, the frequency is very low. So what do these emit? These end up emitting infrared, and that's why these were discovered after Lyman, and these were discovered by a guy named Bastian, so this is called the Bastian series. So we have the Lyman jumps, which are big jumps producing ultraviolet, the Balmer, which are medium jumps producing visible light, and lastly we have tiny jumps, which were discovered by Bastian, and those were the infrared jumps. So here are all the jumps and all of the series at once. So we have the Lyman series on the left, which are ultraviolet, represented in black because you can't see them. The Balmer series, which are our visible spectrum. The Bastian, which are our infrared, which are also not visible. And then there's the other series that we don't have to deal with, which are the smaller jumps from the higher energy levels. Now, I'm not going to go and do examples of these for mercury, but it's exactly the same as hydrogen. How do you do it? Well, if you want to find the jump, you just find the energy level and subtract the difference and do the same process that we did before. So when we look at this, they did make one change. These are called n equals 1, n equals 2, and so on. These are given as A, B, C, D, E, F, G, H, I, J, but it doesn't really matter. The last thing to pay attention to here is the ionization energy. If they ask you to ionize an atom in the ground state, the answer would be 13.6. To ionize an electron. To ionize an electron in n equals 2, it would be 3.4 electron volts, and so on. These are the energies needed to get the electron completely out of the atom.